start a good old recording. Might just be you today. We'll see. Usually more people show up about 10 minutes in. But, so, sort of give me your run through. What exactly are Kirchhoff's two circuit laws? And how do we use them?
So Kirchhoff's circuit laws refer to the amount of current that flows at the node. So the amount of current that goes into the node should be the same that goes out for at least the ideal circuits here.
Yeah, which is everything we'll see.
Yeah, and
So,
then oh, sorry, go ahead.
Yeah, no, go ahead.
And then for the other part of it, then all of it has to add up, or the voltages when you add up the ones that come from the batteries and then how they drop off due to going through the resistors, they all have to add up to 0 for a closed circuit.
And what's not even necessarily specifically the entire closed circuit, what specifically potentially within the circuit?
I don't think I understand the question.
So what if we have a circuit like this, where what's our definition of our entire closed circuit? Is it going through everything individually?
No.
So in what situation would our voltage rule, where voltage being 0, apply?
It would apply for the battery going through the closed, loop. I guess closed loop is a better word for it.
Exactly. That's what I'm looking for. A loop. And so, can it be any loop that you can draw within a circuit? Or does it have to include the battery?
I think it can be any loop.
Exactly. So if we were to go ahead and draw a loop just within R2 and R1, would that net voltage have to be 0?
Yes.
Yep. And if we have it with a battery and any individual voltage, it also has to be 0. So what does that mean about the voltages of resistors that are parallel to one another?
They have the same voltage?
Yep, exactly. That's sort of what I'm going for. Where, I guess in this circuit example, we're always going to have our current. Let's say we're going to assume it always goes around clockwise. So it's going to go down through R1, down through R2.
Mm-hmm.
And so if they have the same voltage drop going down, if we draw a loop within R1 and R2, one is going down and the other is going the opposite direction. So we reverse the sign of the voltage and it comes out to be 0.
Oh, yes, that makes sense. Okay.
Cool. All right. So basically we have our junction law, junction, where you said that the total current in is equal to the total current out, right?
Mm-hmm.
And then for a loop, delta V for a loop is going to have to be 0. Those two laws, plus being able to understand Ohm's law, which, by the way, what is Ohm's law?
I don't know. I actually don't have a good definition for that.
I bet you know what it is, you just don't know it as Ohm's law. It's probably a certain equation you've been using a lot in the last week on your homework and class questions.
Can I have a hint?
It has to do with the voltage for a resistor.
The voltage for a resistor.
It relates the voltage across a resistor to the resistance.
Is it V equals IR?
Yep, exactly. That's what I'm looking for. Yep. Ohm's law, V is equal to I, the current through the resistor, times the resistance of the resistor. Boom. Or if we have the total net resistance in an entire circuit, then we can solve for the current by dividing the voltage of the battery by the total resistance. And that will apply for every single example of something you'll see in this class. There's further things where you have non-ohmic devices that don't follow Ohm's law, but that's a story for another time. For 300 level physics classes, if you're even a physics major, or if you're going into electrical engineering and stuff. So then what would be the power dissipated across a resistor?
That one, the power is related to the current I and the voltage, or it's related to the current squared and the resistance, which is the same thing as just putting in for the voltage.
Yep,
because V
exactly.
equals IR, like we said.
Yeah, P is equal to IV, V is equal to IR, so it's I squared R. What if we wanted to put it not in terms of the current, but instead in terms of the voltage and the resistance?
The voltage and the resistance.
Mm-hmm.
So V equals IR, then V squared over R?
Yep, exactly. Yep, we just plug in I is equal to V over R, plug it in there, V squared over R. Does he actually, I'm pretty sure he gives you that on your formula sheet as well.
No, he does not, but that's easy enough to derive, I'm sure.
Okay, yeah. He does just give I squared R. That's interesting. Oh, welcome. How's it going, David? How's it going, Shadia? We just sort of went through and talked about Kirchhoff's junction and loop laws, where we have the junction, so the total current in at any junction is going to equal the total current out, and then voltage around a loop is always going to be 0. And then we also talked about Ohm's law and the power dissipated across the resistor. So let's go ahead and just hop into some examples, because honestly, the best way to get comfortable with this stuff is to just practice, work on examples, keep hammering it, because there really isn't a way to like conceptually understand anything that happens in this class. You have to get comfortable with practicing it. It's not like, for example, for chemistry, you add one thing to another and it makes sense, it's going to blow up. It doesn't quite work as well in physics. So let's go ahead and take a look at this example. So we're going to have 3 resistors connected to a 10-volt battery, and we have the resistances 100 ohms, 300 ohms, and 250 ohms. And then the battery is also going to have an internal resistance of 10 ohms. So what exactly does that mean? What is internal resistance of a battery? Does anyone want to sort of explain what exactly does it mean by an internal resistance? Or why can we sometimes say that there's negligible internal resistance? Is there such thing as an actual ideal resistanceless battery? Sort of similar to the question, is there such thing as an actual perfect circle?
I guess not.
Yeah, and so basically and the same thing, like there's always going to be at least some sort of resistance in anything. There's no such thing as a truly resistanceless material. Like even conductors have a very small amount of resistance, though generally we can ignore it because it's very small. Sometimes we can't ignore the internal resistance for a battery. And so essentially a 10-volt battery with an internal resistance of 10 ohms can basically be treated as we have our battery basically be treated as we're going to have a 10-volt voltage source here. We are 10 ohms resistor, all contained within our battery. Does that make sense? So let's go ahead and let's take about 10 minutes. I want you guys to go ahead and solve for what would be the current through the battery, and then what would be the current through each resistor. And keep in mind, the switch here is initially closed. What does that mean that the switch is closed?
It means and that becomes like a wire or something.
So does that mean we do have to take into account R3, or is it
Yes.
disconnected? Okay, yep, exactly. Switch is closed. It means R3 is connected to the rest of the circuit. So let's go ahead and take 10 minutes. Let's find the current through the battery, the current through each resistor, and the voltage drop across each resistor. And we'll go ahead and talk about it. All right, so how would we actually go ahead and first off solve for the current that's through our battery? How would we solve for the current through our battery? What law would we have to use? How's it going, Kevin? We're just about to go over A through C here. Sorry to put you on the spot right after you joined, but do you know how would we solve a current through a battery? What would we have to do? What law would we have to use?
Getting my mic situated. Am I heard?
Sure thing. Yep, I can hear you.
Okay. Let's see. We're
Cool.
given resistor.
Yep.
We're giving our resistances and the voltage. So
Yep.
I mean,
So how
it'll
would
be as simple as finding the, I forgot the word, equivalence, resistance equivalence between R1, R2, and R3.
and then what
and,
law do we use?
Shoot, I won't be able to name the law, but it's an equation, so.
Yep.
But
And then how would we actually go ahead and solve for the current?
well, I tackle it with we know that. Let's see, between R3 and the middle path, that's in parallel.
Mhm.
So we'd use let's see, the parallel equation for like R3, 1 over R3 plus, in parentheses, that little section that we're just gonna like deal with, on the inside of those parentheses, I'd say. So
Mhm.
yeah.
So
Yeah, we do R12, yeah. And then I guess we say that, R12 would also be,
parallel.
yeah, they would be parallel between each other.
So if R3 is parallel to R12 and R1 and R2 are parallel to one another, wouldn't that make R3 also parallel to R1 and R2?
That's an interesting thought. I
So couldn't we just do this?
right. Definitely, it was pretty misleading how it was structured, but I think that's
Yeah.
exactly the same.
Yeah, it is exactly the same. Because the reality is, it doesn't make a difference. With our wires, we can, like, redraw our circuit however we want. We can move the connections of our wires around as much as we want along any path, as long as we don't change the actual orientation of the resistors. So, like, if we draw it like this, or if we want to draw our circuit like this, where we have if we like went ahead and moved the connections for R2 all the way over to here, it'd be the exact same thing. It's a bad drawing, but just to sort of visualize. But so we get our total net resistance for R1, 2, and 3. Is there any other resistor? Is there any other resistance we need to take into account here?
No. I
No.
don't think so.
Isn't there an internal resistance inside the battery?
Oh, okay. I didn't read that.
I thought you said it was negligible.
Well, in some examples, it is negligible. In this case, we're going to say it's not, and we do have to take it into account. And we'll find at the end that if we had ignored it, it would still be pretty close to the right answer, but it's not quite negligible.
So how do you know when it is and when it's not?
In this class, if he tells you the internal resistance of the battery, you can assume it's not negligible. And if he doesn't tell you, then we can ignore it.
Oh, okay.
So basically, anytime if the problem says internal resistance of whatever, I would treat it as if it does matter, and you do have to take it into account.
In such case, you're just added 10 for RNet plus 10.
Yep, exactly, because it's in series with R1, 2, 3. Plus, we'll call this R battery, RB. So we go ahead and find this total net resistance. So we have 1 over 100 plus 1 over 300 plus 1 over 250 to the negative 1. Has anyone actually calculated that? Did anyone get a value of about 68 ohms? 67.7 ohms? We did 1 over 100 plus 1 over 300 plus 1 over 250 to the negative 1. Then we added our 10 ohms for our internal resistance of our battery. We get total resistance of about 68 ohms. So then how do we go ahead and solve for the current through the battery?
We use Ohm's law, so V equals IR, and the V for this is 10 volts, and then using the equivalence resistance that we just calculated.
Yep, exactly. I is equal to V battery over R net, which obviously we go ahead and just divide our 10 volts by our 67.7 ohms. We should get a current of about 148 or 0.148 amps. So I'm going to call it 148 milliamps. Everyone else get that? All right. So then how would we actually go ahead and calculate the current through each resistor individually? Do we actually know the total voltage drop across each resistor?
Yeah.
And what would it be?
It's all the same, so it'll be V.
It would be...
Minus the resistance, right? Because it has a resistance.
Yeah, so we have to take into account the internal resistance of the battery.
Yeah, so it'll be V. It will be V, which is I times R, which is I times 10. Right?
Not quite.
Not quite. Okay.
Well, that would be the total, like the difference between the 10 volts and our...
I meant V, which is... Okay, so it wouldn't be that.
So, how do we solve for the total voltage drop across our battery, including the internal resistance? I think we actually call it epsilon, though. Is it? Does he not have it in... Huh. Oh yeah, he is giving you it. So essentially, what we want to go ahead and solve is the voltage across the terminals of the battery. In past semesters, we called it epsilon, but I guess he's just calling it V terminals now. So how do we go ahead and solve that? So as David said, we take our voltage of our battery, the ideal voltage, which is our 10 volts, and then we would subtract the voltage that's being dissipated across our internal resistance, which is the current through the battery times the resistance within the battery. So if we go ahead and calculate that, we multiply our current that we solved for times our internal resistance, and we subtract it from our 10 volts. We get a voltage across the terminals of about 8.52 volts. Did everyone else get that? So now that we have our voltage across the terminals, how do we get the voltage across each resistor? How do we get the voltage dissipated across each resistor?
It'll be that then. It'll just be 8.52, right?
Yep, exactly. And why is that?
Because they're in parallel.
Sorry, what was that? I couldn't quite...
Because they're in parallel.
Yep. And what Kirchhoff law do we use?
What do you mean? Oh, I can't think of it. Oh.
But
I'm not sure what to ask him.
I mean, you're absolutely right. Because they're all in parallel, then they're all going to be the same voltage, and it's going to be the voltage of across our terminals of our battery. But does anyone know how we actually, if anyone doesn't quite understand that, how would they be able to reach that same understanding?
Would it be?
Oh, okay, I see what you mean.
Go ahead, Kevin.
I don't remember what it was called, but the fact that like the voltage gained is equal to the voltage drops. So
For what?
for I guess I don't know what.
A closed loop.
Yep.
Closed loop. Yep.
Any closed loop in the circuit. So let me actually go ahead and want to get this image over here. Boom. So if we go ahead and take a look at our circuit, we can use this loop law where the voltage around any loop, or I guess it looks like it says bop, but whatever. The voltage around any loop. So we can draw a loop through the battery plus 8.52 volts. And then just through R1 minus 8.52 volts. Or battery plus 8.52. R2 minus 8.52. Or R3. Same thing. Plus 8.52 minus 8.52 through R3. So the voltage across each of them is 8.52 volts lost. So then how do we solve for the current through each? What law do we use?
Isn't it KCR?
Say that again?
Is it KCR? Or the first one that you have, IE, IL?
Wait, are you talking V equals IR?
No, I said KCR.
KCR?
Yeah, I think it's like Kirk. I mean, they had it in like the worksheet this morning. Never mind that I'm confusing you.
Yeah, it's not as complicated as you think. It's something we actually already used to solve for our current through the battery.
So it would be the summation of the current in, summation of the current out.
Sure, we could do that, but that's annoying. There's something a lot simpler I'm looking for here.
So V equals IR then, because we already know the voltage and the resistance.
Exactly. Boom. We literally, we don't even have to worry about Kirchhoff's junction law here. We can just use Ohm's law. V equals IR. We know the resistance across, we know the resistance of each resistor, and we know the voltage across each resistor, so we can just solve for the currents. And then we could obviously go back and double check. Do our numbers actually make sense? Oh, yep, they do. And we can check them using the junction law. But so then we know for each individual resistance, we'll call it IN for I1, I2, I3, is going to be the voltage across the terminal divided by the resistance of that resistor. So then I1 would be our V terminal divided by R1, which is 100 ohms, so about 85 milliamps, 0.085 amps. I2 would end up being divided by 300 ohms. We get about 28 milliamps, 0.028 amps. And I3, it's the same thing, but we go ahead and divide by 250. We get about 34 milliamps. Right, that makes sense. And we can actually go ahead and double check these numbers using the junction law to make sure we actually got the right numbers, the right currents. So if we go ahead and we have the current through the battery here, which is, we'll call this IB. So we have IB. And then IB is going to go ahead and split here at this junction into I3. And then we'll call it I12, just to make things easy. And then I12 then splits into I1 and I2. So I12 is going to be I1 plus I2, so we can check that. That comes out to be about 113 milliamps. So then we know that IB is going to be I12 plus I3, so 113 plus 34 milliamps. We get 147 milliamps, which close enough to 148 because we were rounding, and this is like 28.4, this is 30 point something, this is 85 point something. So use the junction law, and we double check that we got the exact same currents as we would expect. And someone mentioned actually using the junction law to solve for these currents. How would we actually go ahead and do that? Because that would be a bit more complicated, but how would we actually do that?
Use Kirchhoff's current laws.
And so what would sort of be the general process?
I guess pretty much what like to like pick a node, I guess, and where all the currents are going through, whatever. I don't know if you get what I'm saying. So it would be like pretty much currents going in equals current going out. So
But so how would we actually be able to understand anything about the currents? What would we have to do first?
what would we have to do first? Where? Like, I don't know.
There's another law we would use first.
Oh, the voltage law?
Exactly. And so what would we do?
Okay, so... Oh, okay, because I think in the worksheet he used to look at the voltage law first, I guess. But don't you just like pick a node and then it would be like a resistor would be like, I'll draw a loop in each like box, I guess.
Exactly.
Should we like combine R1 and R2 before we draw the loop? Because that would give us like 3 loops in that sense. Or 3, like, you know what I mean?
Well, it doesn't matter what we do. There's actually, I mean, how many loops could we draw? We could draw battery R1, that's one loop. Battery R2, that's another loop. Battery R3, that's a third loop. We could also draw R1 and R2. We could draw R1 and R3. And we could draw R2 and R3. That's 6 different loops we could do. And how many unknowns do we have? We only have 3 unknowns, so we actually don't need to draw all of the loops.
Right.
If we have 3 unknowns, how many equations would we need to make?
3.
Yep, we just need 3 equations. And so what we know is, let's just take the simplest example. Let's go ahead and draw one loop for R1. So it would be plus V terminal across the battery minus I1 R1 across the resistor would have to be 0, right? And the same thing for if we wanted to have, minus I2 R2 or minus I3 R3. So those could be our 3 equations. V terminal minus I1 R1, minus I2 R2, and minus I3 R3.
I don't get why you're doing... can you show us how you're getting the I2, R3? How do you know it's doing this?
So essentially, let me go ahead and get a fresh little image here just to visualize. So for each of these equations, I'm essentially, I'm just going to add the plus V terminal. Plus V terminal. So for each of these equations, I'm essentially starting at an arbitrary point. Let's start here right before the battery, and we draw a loop. We go through the battery. That's our plus V terminal. And then we're going to go along here. For the first one, we're going to go down here and go through R1. And we know the voltage across R1 is going to equal... Well, first of all, it's going to be a negative voltage. That's why we have the negative sign, because we're losing voltage. We gain it across the battery. We lose it across the resistor. And we know that this voltage is equal to the current through R1, so we'll call it I1, times the resistance of R1. So V terminal minus I1R1, and then we complete our loop.
Sorry,
there's-
if you don't mind me asking, can you draw the signs of the voltage and the resistors? Is
What do you mean signs? Like,
you know how they have sometimes like a plus and a minus? Like
Um,
what would you like when they were doing their examples? They have like the plus and minus.
oh, for the battery or for the resistor?
Both.
Well, for the battery, we have the positive side here, and then we'd have the negative side
Mm-hmm.
on the other side. And so then we know that the resistor is going to be in the opposite direction, so that as we go across it, we're going in the opposite direction, so we're losing voltage.
Okay.
So essentially, all we've done is we've guessed that our current is downwards for all three of these. And if we were to solve it and get a negative value, which we didn't for this example, but let's say we did, if we found a negative current, what would that mean?
Yeah, we drew out our arrows incorrectly.
Yep, so that just means the current would be going upward, for example. Does that make sense? Oh crap, have I screwed myself here? I may have just screwed myself. I can't undo things that far back. Uh-oh. Well, I guess we can't see our answers anymore, but but we know how we got them. And I'll try to figure things out later. So we've found our current through each resistor, and we've found our voltage drop across each resistor. Now, if each resistor were a light bulb, which one would be the brightest? Which resistor, which light bulb would be the brightest out of these three resistors? Does anyone know how we would figure that out?
I think it'll be R3. Right?
And how did you come to that conclusion?
I think the realm, I guess I would think about it is R1, R2 would combined, and there would need to be like a stronger voltage to kind of, I forget how she explained it, but there would need to be like a stronger voltage to accommodate R1, R2 versus just R3. Oh, wait.
I think you're overcomplicating it a bit.
Oh, okay.
I would use the power equation. Just compare the voltage drops we have and the currents for each resistor.
Yep, exactly. That.
So whichever two are higher would be
the brightest.
The brightest, yeah.
Yeah, exactly. So we can use our power dissipated across a resistor, which is IV, or I squared R, or V squared over R. And we can go ahead and solve for the power dissipated across each resistor, and whichever one has the highest power is going to be the brightest. So P is equal to IV. So P1, what's the current across I1 again, because I accidentally covered it up and I can't undo that far back in Paint. It was something like what, 20. Let's see, I2 was 28 milliamps, I3 is 34, and then what was I1 again?
Don't remember.
Come on, guys, you gotta be writing these down. I think it was, I'm pretty sure it was 85. I just did some mental math in my head. 85 plus 28 plus 34 has to be our current through a battery, which is 148. So P1 is IV, which is 85 milliamps times the voltage. And we could do the same thing for P2. And the same thing for P3. So, which one would be the brightest? We don't even need to calculate any numbers here. Aren't the voltages across each resistor the same?
Yep.
So-
So one would be the brightest.
Yep. R1 would have to be the brightest because it has the highest current. So P1 is the brightest, and we could actually go ahead and solve for the powers. It's going to be about 0.72, I think, watts. And then for P2, it's going to be about 0.24. And then for P3, it's going to be about 0.29. So yeah, P1 is the largest power, which means the R1 would be the brightest light bulb if it were a light bulb. Does that make sense? Anyone have any questions about this?
As far as like them being in parallel, if there is like another structure, there would be like a situation where the one with the least resistance isn't necessarily the brightest. Maybe, I don't know.
Well, if
Because like my initial like way of thinking was just like go with the one with the least resistance, but I know that isn't always the case.
so, if everything's in parallel with each other, meaning they all have the same voltage drop,
Right.
then yeah, the one with the least resistance would have to be the one with the most current and therefore the most power. But if we go ahead and we have resistors that are in series with one another, as well as some resistors in parallel, then we might have an example where the lowest resistance is not the brightest. And you just honestly don't try to think of things conceptually. Nothing in this class makes conceptual sense. And if you think you found something that sort of makes conceptual sense, like, oh, lowest resistance equals highest, brightest means brightest, well, eventually you're going to find something that is an exception to that rule, and you're going to be like, damn it. I guess I can't use that conceptual idea anymore. And that's the case with a lot of physics. There's nothing that really makes conceptual sense. But what does make sense?
I think I'll quote you on that.
Yeah, nothing in physics makes sense. Quote me on that. Nothing in physics makes sense. This isn't even, you guys ain't even seen shit. Just wait till you get into, if you're a physics major, just wait till you get up into quantum mechanics. Oh, God. But yeah, nothing in physics makes sense, but the math works. Trust the math. Praise be to the formula sheet. Worship it every night. Learn to love it. The math, as long as you know how to use the equations and calculate things, the numbers won't lie. You might be like, I don't totally get it, but you calculated it with the equation, and as long as you did it right, you'll have the right answer.
Amen to that.
So, let's go ahead and let's open the switch. So we're going to go ahead and disconnect R3 from the circuit. So, I don't really feel like... do we really feel like going through and calculating the current through the battery and the current through each resistor and the voltage drop again? Do we want to go through that again? Because it's pretty much the same thing, but we just ignore R3. So, let's just talk about what would happen. So, if we go ahead and disconnect R3, is the current through the battery going to increase or decrease?
What do you say? I'd say increase.
And why do you say that?
Well, if the let's say we have R3, if you take that out of the total current, then it'll just go to the other two resistors. I mean, two paths.
You know, it really is a sad day today. It took you all of a minute to forget the one doctrine we were just going to quote me on. Nothing in physics makes sense!
I understand. Okay.
So,
What was the question again?
So, is the current through the battery going to increase or decrease when we disconnect
not
R3?
through the battery. Yeah. No, I'd say the current through the other two resistors would increase, but not through the battery.
Once again.
I wasn't listening. No, it doesn't make it. No, it won't.
No, it won't make sense like that.
It won't make sense. Okay.
Or maybe that might be the right answer, but I know the logic you're using isn't quite sound. And let's actually sort of like think through it for a second. So
I mean, I know that the total, resistance would change, like the entire formula we did like earlier, but that would change, and that would go into, the total current.
Yep.
I just don't exactly know the nature of that, so I guess you just have to do the math first before you say it.
Yep. We would have to do the math. But so basically what would happen if we go ahead and ignore R3, then 1 over R3 gets removed. So we just completely ignore that. So that means that this 1 over R1 plus 1 over R2 goes down, which means the actual R12, R net is going to go up because we have to take the reciprocal. Does that make sense? I don't know, my wording's a bit weird. But basically, if we have like 1 over 5 plus 1 over 2 to the negative 1, or let's do 1 over 4 plus 1 over 2. 1 over 4 plus 1 over 2 to the negative 1 is going to be 3 over 4 to the negative 1 is going to be 4 over 3, so about 1.3. But if we ignore the 1 over 4, then 1 over 2 to the negative 1 ends up being 2, so it actually goes up. Does that make sense?
Yes.
So by removing a resistor, the resistance goes up.
I have a question.
Yep.
So on the quiz, right? Sometimes we don't always get numbers for the different circuits and opening and closing them. Should we just like arbitrarily assign like a number to it and then try to figure it out by taking one of them out?
If that helps you understand it, I mean, like how I'm doing here, absolutely do that. Whatever it takes to actually understand what's going on.
Okay, cool. Sounds good.
Yeah. So basically, by taking a resistor away, we increase the total resistance of the circuit. See what I mean? Nothing in physics makes sense.
I completely understand.
But so we know that the total resistance goes up. So that means the current through the battery has to go down. Right?
Yep.
And so the current through the battery goes down, which means our V terminal, which this thing's still in the way and it freaking sucks, but how V terminal is equal to VB, which is a constant, minus IB times RB, the resistance inside the resistor. So if the resistance goes up, this current goes down, which means our V terminal would go up ever so slightly, not by much. It might go from like 8.5 volts to like 9. It's not going to be much. So what does that mean about the currents through R1 and R2? Are they going to increase, decrease, or stay the same? If V terminal goes up,
It'll decrease.
decrease.
I
Why?
think so.
Why is that?
I'm just looking at V equals IR, and I think that's how it goes.
Uh huh. And so V equals IR. You're right. If V goes up and R doesn't change, V goes up.
I would have to go down.
No, I would have to go up.
Or it would. Oh, okay. Never mind.
They're on opposite sides here.
Gotcha.
Yep. So there you actually sort of you knew to go to the equation, but then you just failed 6th grade math or something.
Yeah.
Nah, happens to the best of us. Everyone forgets negative signs or forgets how numbers work on exams and stuff. So then we know that V terminal is going to go up. So the current through the battery goes down, and the current through I1 and I2 are going to go up slightly. And then same thing as before. If each resistor is a light bulb, which one would be the brightest? Once again, in this example, it would have to be R1.
R1.
Yep, because highest current. It's going to have a higher current than R2. So let's take a look at one more quick example here. Or quick. I'll give you guys like 10 minutes to work through it. But we have 3 batteries here with voltages, 12 volts and then 6 volts for the third battery, and negligible internal resistance. We don't have to worry about internal resistance here. And they're going to be connected as shown with 3 resistors. So let's go ahead and find the current through each resistor. So apply your Kirchhoff's loop laws, junction laws, Ohm's law, whatever you need to do. Let's take 10 minutes and then we'll go over it real quick right before we finish up. If you have any questions, feel free to ask.
I mean, obviously, like, many times more simple than the examples we've done so far, because there's not a lot of time to really do all these calculations in your head, right?
Yeah. So quizzes, it's going to be a bit simpler. Like, I think a problem like this here would be a problem like this would be reasonable for you to do in about 15 minutes.
Mm-hmm.
So it might be like, this problem would be like an entire one quiz, or like this plus like 1 or 2 other questions, or like, asking you what's the power through a resistor or something.
Okay, so for like a quiz, we would only see like 2 or so resistors in like series or in parallel, and then try to figure out. I mean, for the light bulb ones, because that's the ones I feel like are really difficult for me at least.
Yeah, I don't want to give you an exact answer and be like, absolutely, you're not going to see anything more complicated than this or whatever.
No, but I mean, like, with 3 or more, then it starts getting really complicated understanding how the relations are to each other, and then, like, which ones are, like, which ones have the equivalent voltage or, or current and stuff.
Yeah, so
I'm saying.
I know that, so when Goolsby Cole taught this class a year and a half ago, fall 2019, when we were still in person, I was doing SIPass. The quizzes for this week, the quiz that he did on Friday for this week was like, it was like two resistors that were in series with one another, and then a third resistor that was in parallel with both of them. So it was like R1, R2, R3, and then a battery. It was something like that.
Okay.
And you should be able to apply your loop laws to be able to figure out which one would be the brightest.
Okay, sounds good. Thank you.
No guarantee it's going to be the same question or whatnot.
No, that's all good. I'll study the same I studied all the other weeks. I was just wondering what I might be able to expect on there. But that's cool. Thanks.
Yep. How's it going, Basil? We're going over this problem right here. So we have our 3 batteries and 3 resistors. And we're going to be going over it in about 5-6 minutes here.
Gotcha. Can you hear me?
Yep, I can hear you.
Okay.
Yep, go ahead.
So if the current on R1 was moving towards the right, and R2 was moving downwards, and R3 was moving to the left, then would that be on Kirchhoff's current rule, I1 plus I3 equals I2?
So, hold on, let me visualize. So we have I1 to the right,
Mm-hmm.
and then like R2 down, and I2 down, and I3 to the left, something like that.
Yep.
Coming
Yep.
into a loop. So what's the total current coming in?
I don't understand. So are you saying...
So what's the total current that's going into the loop and not leaving it?
Well, I1 is going into the loop.
Mhm.
I3 is also going into the loop.
Yep.
And I2 is also going into the loop.
Well,
Or
It's
the
going-
loop is... I see. Okay.
it's going out of the junction.
Right.
So in this case, I personally, so he has it written as the sum of I in is equal to the sum of I out.
Mm-hmm.
So the way I would put this is I1 plus I3 going in is going to equal I2 out. And then you could move I2 to the left side where it's I1 plus I3 minus I2 is equal to 0.
I see. So if I say I1 was going to the left instead, would that, and I2 were going up, that would be I3 plus I2 equals I1.
Yep,
Okay,
exactly.
I see.
And once again, it really doesn't matter how you define what directions your currents are going. Just arbitrarily choose it. All right, this current's going this direction or whatnot. And then when you solve everything at the end, if you get a negative value, what does that mean?
That's in the opposite direction.
Yep, exactly. So in a theoretical example, if we solved for I1 and it was negative, it means it's actually to the left.
Gotcha. Okay. Thank you.
Let's take about 4 more minutes, then we'll go over this problem right here. So, how would we start approaching this problem? How would we go ahead and find our currents through each resistor? So, let's just arbitrarily define directions for our current. What direction do we want I1 to be in up here through R1?
To the right.
Yep, let's just say it goes up and to the right. Call this I1. What about I2 here? Do we want this going up or do we want it going down?
I guess down.
Yep, let's just say it goes down. We have I2. And then for I3, do we want it going up or down?
Up.
Sure. All right. So we have our 3 currents, I1, I2, and I3, and that's what we want to solve for. So now we have 3 unknowns, so we're going to need 3 equations in order to solve for them. How do we get these equations?
Use Kirchhoff's laws.
So what are Kirchhoff's 2 laws again?
Voltage and current laws.
So what's the voltage law?
The voltage across something goes to 0.
Voltage around a loop is going to be 0.
Oh, no, it goes to 0.
So let's draw a loop, and we can set the voltage equal to 0. Let's go ahead and let's do one loop here. So over here on the left side of the circuit. Right? So we'll start right here. Go up. We have plus V1 we go through here. We have minus I1R1. We go down through B2, through V2, and we're going opposite of the direction of V2, so it's going to be minus V2, then minus I2 R2.
Wait, why did you have I1 R1 as minus?
Because we're going along the direction of I1.
So that's not positive?
No. So the voltage across a resistor is always going to be negative because it's a voltage drop.
Okay.
Yeah. Or another way, we can go ahead and draw like plus and minus signs for the terminals for the
Yeah, that
resistor.
usually helps me.
Yeah.
Like, maybe. Yeah.
So for a battery, the plus side is always in the direction of the current. And for a resistor, it's always against the current.
Gotcha.
So what would be the plus and minus signs for R3 over here? Is the top going to be plus or minus?
So it says always minus.
Yep.
Okay.
Minus and plus. And for R2, obviously
Yeah.
plus minus. So we have our total voltage around this loop. And we know that has to equal 0. Let's go ahead and draw another loop. Let's start right here. So we'll start here and we'll go up through V3. So plus V3. And then we go up through R3. So it'll be minus I3 R3. Go around here. We'll go down through V2. So minus V2. And then minus I2 R2. And we come back to our original location. And we know it all has to equal 0. Now, we need one more equation to be able to solve for our currents. We have 2 equations, but we have 3 unknowns. How can we get a third equation?
Kirchhoff's current laws.
Mm-hmm. And what's the current law?
The sum of all currents passing through a node. I guess.
Yep. So the total current going into a node has to be the total current out of a node. So let's choose this node right up here. We have I1 going in. Plus I1. We'll just say I1. I1 going in. We also have I3 going in. And then we have I2 going out. And here we have literally everything we need to solve this problem. And we know our voltages, we know our resistances. Those are numbers. So we can actually go ahead and rewrite these. So we have plus V1, which is plus 12, minus I1 R1, which is 800 I1, minus V2, so minus 12, minus I2 R2, minus 300 I2. For the second one, plus V3, which is 6 volts, minus I3 R3, which is minus 300 I3. And then we have the same minus 12, minus 300 I2. So now we just need to apply some algebra in order to solve for these. This algebra is going to be annoying. It's going to take up half a sheet of paper. Has anyone here taken linear algebra? Math 221?
Mm-hmm.
What could we use to solve the system of equations, or find something to solve the system of equations for us?
Matrix?
Exactly. We can use a matrix. So, easy, quick little thing that anyone who hasn't taken linear algebra don't have to worry about this too much. But it takes about 10 minutes to learn. It's super easy, and it will save you so much time on your exams. Like, this system of equations would take me probably 5 or 10 minutes to solve by hand, actually going through and doing the algebra myself. Matrix, we create our matrix, and you can plug it into Symbolab, and it solves it in 2 seconds. So the way we create our matrix is we essentially want to rewrite each of our equations in terms of all the I1, I2, and I3 values on the left and our constants on the right. So this first equation would be minus 800 I1 minus 300 I2 is equal to, and then we have 0, and we move our 12s. Our 12s cancel out, so it ends up being 0. And I'm also going to say we have plus 0 I3 equals 0. For the second one, we have 0 I1 minus 300 I2 minus 300 I3 is equal to, we've negative 12, 6, negative 6, move it over to the other side, we have 6 volts. And for the third one, it's obviously 1 I1 minus 1 I2 plus 1 I3 is equal to 0. So then what we do is we'd create a matrix where we take each of these values. So it's going to be a 3 by 4 matrix. So we have all our values we'll plug in here. So we have minus 800. This is the I1 column. Minus 800, 0, 1. Minus 300, minus 300, minus 1, 0, minus 300, plus 1, and then our fourth column is our constants, which is 0, 6, 0. Then, if you've taken linear algebra, you would reduce this matrix down to its row-reduced echelon form. Screw understanding whatever the hell that means. I'm just going to use Symbolab. So we have a Symbolab math solver. Literally just, you can go ahead and create a matrix. Where's the matrix button? Nope. Where is it? It's been a few months since I used Symbolab. Hold up. Lab matrix solver. There we go. So we want a 3 by 4 matrix. We just plug the values in. 0, 1. Highly recommend do this on your quizzes on Friday. It'll save you about 5-10 minutes. Negative 300. Negative 300. Negative 1, 0, minus 300, 1, 0, 6, 0. Just hit go to solve it. And essentially we want our row-reduced echelon form right here. And so we have 1, 0, 0, 0, 1, 0, 0, 0, 1. And then our values here over on the right are our 3 currents. So I1 is equal to 3 over 950 amps. I2 is going to be negative 4 over 475 amps. And I3 is equal to negative 11 over 950 amps. So David, you guessed wrong for the directions of our currents.
Oh no.
What the hell? God damn it. Yeah, so we've solved for our values for our currents, and we know that because I2 and I3 are negative, I2 is actually upwards and I3 is actually downwards. Cool. Does that make sense? Anyone have any questions about this?
So wait, if we get the negative then and we change directions, do we just change it into positive?
What's that?
So, because like if I put in negative, like let's say like this was like a test question, and then for I2 I put in negative 4 over 475, would that be wrong?
So I would guess that on the quizzes he's going to have you just enter magnitudes. Or he's either going to ask you for magnitudes of currents, so just put in the positive value, or it's going to specifically say what's the current through I1, treat right as positive, or what's the current through I3, treat upwards as positive.
Right. So I'm guessing in this case, would you just multiply by -1 to find the quote-unquote actual current?
Could you say that again?
Would you just multiply by -1 then, since it's going down versus?
Yep.
Oh, okay.
Yep, all you have to do is change the sign.
Oh, okay.
Yep, so I2 being
But
negative.
the actual magnitude is correct. It's just the sign missing.
Yep, exactly. If we solve for a magnitude here, so if we get negative 4 over 475, that is the magnitude. The magnitude is 4 over 475, and the direction is upwards, because we guessed downwards, and we got a negative value.
Got you. Okay, thank you.
Anyone else have any other questions? All right. Well, in that case, I was going to wrap it up for today's session. Hopefully, this helped you out a bit. We'll have more practice on this tomorrow before your quiz Friday. And if you have any, I highly recommend, this is like the main thing I recommend, figure out how to use this matrix row reduction thing, because it's super easy to mess up on the 6 steps of algebra you do to solve these problems without the matrix. And the matrix will save you like 5 minutes anyway, even if you were doing it optimally without making mistakes. So, hope that helped out. Thanks guys for coming. If you didn't already, if you could fill out the attendance form, it'd be greatly appreciated.
The attendance form.
So it's in announcements. The announcement I send out, I link the Google form to fill out attendance.
Okay.
I can also put it in the session text chat if anyone wants to find it there as well. All right, thanks everyone for coming. Hope this helped out.
See you.
Have a good day, everyone. Same time tomorrow.